So our next topic when dealing with sequences are these things called recurrence relations. And recurrence relations um, are ways of actually iterating or talking about sequences that reference the previous terms or a set of previous terms inside of that sequence. So for example, a recurrence relation for a sequence AN is an equation that expresses AN in terms of one or more of the previous terms of the sequence. So we've got AN, right, is our current term. A naught generally is the first term or the initial term of the sequence. So that's another way to look at that. Then, and this is kind of tricky, a to the n minus 1. All right, so notice we've got n, we have the nth term, and then we have the n minus 1th term, okay, is the term right before an. Before an. Okay, and then we might say a to the n minus 2 is right before a to the n minus 1. So it's 2 away, right? It's 2 before a to the n. So just to kind of give an example of what that might look like, okay? Suppose we had 2, 10, 20, 40, 80, 160. And say, for example, we were on, right, an equals 80, okay? A to the n minus 1 is then going to be 40 because it's the one right before 80, okay? A to the n minus 2 is going to equal then 20 because it's 2 away from 80, okay? And that's actually how we write it, right? And so what we're going to do as we talk about recurrence relations is we're going to learn how to kind of write sequences in terms of the recurrence relations, right? But you have to understand that an is the particular term that you're on, a to the n minus 1 is the one right before it, and then a to the n minus 2 is the one right before that one. Okay, and that kind of those kind of symbols could sometimes be a little confusing. All right, let's take a look at an example. All right. Okay, so let's take a look at an example. Let's say, for example, that I have I'm going to write a recurrence relation. I'm going to say a to the n equals a to the n minus 1 plus 3. And what this is saying is take the last term, the one you just, and add 3 to it. All right? That's basically what we're saying inside of the recurrence relation. Now, here's the thing though. Well, great. I'm going to add 3 to it, but it's still not going to tell me enough about my sequence. What I'm going to need is I'm going to need an initial value. I need a value to start with. Okay? So I'm going to need an a naught, and I'm going to say that a naught equals 2. All right? Now I can actually find it, right? I'm going to say, all right, well, a naught equals 2, and then a1 is going to equal 2 plus 3. And then a2 will equal 2 plus 3 plus 3, right? Because this was a1, yes? So in other words, that's 5 plus 3, okay, which equals 8. So we have 5, 2, 5, 8. A3 is then going to be 8 plus 3, which equals 11. And so on and so on and so forth, okay? So sometimes this is really, really handy because it allows you to just kind of think through how a progression works or how a sequence is going to work. Sometimes a little less handy because, like, say, for example, what is the 37th term of the sequence? Well, in that case, if this is all we know, then the problem is that I'm going to have to write out 37 terms of the sequence. That might take a long time. I mean, 37 might not be terrible. It's no fun, but it's not. Find the 7,000th term. Yeah, that's no good. That's no fun. All right, we don't want to do that. So consequently, what we're going to do is we're going to need to find another way to actually write out these recursive relations, and we will in just a moment. All right, now let's take a look at another example. Let's take a look at an example where instead of just one value, we actually want to think about two values. Let's say, for example, that we've got a to the n is going to equal 3 times a to the n minus 1 plus 2 times a to the n minus 2. All right, great. Well, and let's say, oh, well, you know what? I need an initial condition. I'm going to need a naught equals 1. Okay, great. Well, let's start. So a naught equals 1. A1 equals 3 times 1 plus, 2 times what? Right? A1, if I have A1, a to the n minus 1 is a naught, but I don't have an a to the n minus 2. I've got a problem. So because I have these two terms, a to the n minus 1 and a to the n minus 2 inside of my recurrence relation, that means that I'm actually going to need two initial conditions. Okay, so this is actually not correct. This is not going to work. All right, I'm actually going to also need a1 to equal, let's say a1 equals 1 as well. Okay, so now I have my two initial conditions because I have the two terms in my sequence. So a naught equals 1. A1 will then equal 1, right? Because that's actually defined for me too. A2 is going to equal 3 times 1 plus 2 times 1. So that's 5. A3 is now going to equal 3 times a to the n minus 1 is 5. That's the immediate previous term, plus 2 times 1. So this is 15 plus 2, that's 17. A4 is then going to equal 3 times 17, right? Because that's the previous term, plus 2 now times 5. So 3 times 17 is 51, plus 2 times 5 is 61. Okay? And so on and so on and so forth. All right? In this case, we're going to actually define our recurrence relation using two previous terms. And in order to do that, I'm going to need two initial conditions, right? The first and the second term, right? Or if I say, for example, I had a to the n minus 1 and a to the n minus 2, I might actually, or a to the n minus 3, excuse me, I'll need the first three, right? I'll need a naught, a1, and a2, right? Because I'm going to need to start at a3 and define it in terms of a2 and a naught, okay? So that's actually like whatever this value is, the biggest value inside of your recurrence relation, like in terms of n minus whatever that value is, that tells you how many initial conditions you're going to need, okay, in order to actually develop the recursion relation. All right. Now, let's take a look at one more, and we're going to look at this special one, and it's called the Fibonacci sequence. So you've probably done some work with the Fibonacci sequence. It's a very valuable sequence, okay? And the Fibonacci sequence is defined as a recurrence relation. It is an equals a to the n minus 1 plus a to the n minus 2. All right, and so what we'll notice, it's the addition of the previous two values inside of the sequence. All right, and that means that we're going to need two initial conditions. I'm going to get a naught equals 0 and a1 equals 1. Okay, in your book, they call it fn, and they say that fn minus 1 plus fn minus 2 to define it as the Fibonacci sequence. And so we notice like a naught's going to be 0 as defined, a1 will equal 1, a2 will equal 1 plus 0, which equals 1, a3 will thus equal 1 plus 1, right? 1 plus 1, which equals 2, a4 will then equal 2 plus 1, which equals 3, a5 will equal 3 plus 2, which equals 5, and then so on and so on and so forth. We'll just add the previous two terms, and that will actually give us the terms of the Fibonacci sequence. Okay? So that kind of defines for us some information that we need about recurrence relations. A recurrence relation, as we stated before, is an equation that expresses an in terms of one or more of the previous terms of the sequence, right? We're going to talk about an, and then the previous terms are defined as like a to the n minus 1 or a to the n minus 2. They tell us how far away in the sequence we should be looking for that previous term, okay? So that concludes our discussion on recurrence relations. In our next video, we'll talk about solving recurrence relations, which is in fact a really handy way of going about answering this particular question, like what is the 37th term of the sequence?